All right, so 6.1, composite functions. Chapter 6 is a conglomerate of a whole bunch of stuff. We start off with composites and inverses, and then we move on to logarithms and exponential functions. So the first half of the chapter is very different than the second half of the chapter, so I'll just let you know that. So composite functions are when we put a function inside of another function. So that's all a composite is. So given two functions, f and g, the composite function denoted by, so to read that, it's f composed with g. So that little circle is composed with. And that's defined as f composed of g of x equals, so you put g of x inside the function where every x is. So to form a composite, you put the second, my autocorrect there when I was typing, you put the second letter, that function, whatever it is, into the first function for every x and solve. So the domain is the domain of the composite, so that's the domain of g of x, and then the domain of f of x equals to g of x, then solve. That's a lot easier to explain when we actually go over a problem. Finding domain is not tricky. It's just the wording of it is a little tricky. All right, let's form composites. Let's just jump right in. So we have example 1. We're evaluating a composite function. Suppose that f of x equals 2x squared minus 3 and g of x equals 4x. Now we want to form a whole bunch of different types of composites. So the first thing we want to do is put the second letter into the first one. So that means we're going to put g of x inside f of x where every x is. So f composed of g, and don't worry about that one. We'll worry about it afterwards. So we have our function that's 2x squared minus 3. The x we're putting in is whatever g of x is. G of x is 4x. Do you have any questions on how I did that? Sorry, we have 4 times to go over it. So it's okay if you don't get it 100% right now.
So basically, whatever gx is, you're going to replace it in wherever you want.
Yep, so the second one always goes in the first one. Yep.
Wait, so is that the full answer?
Oh, no, we're not done yet. No, that's just making the composite. So you see how we have this 1 here? What do you think we're going to do with the 1? Plug it. No, we're going to plug it in.
Oh.
Yep. So we have
X.
4x. Yep. So we have 2 times 4x, which is 1. Good. Squared minus 3. So 4 times 1 is 4. 4 squared is 16. So we do 2 times 16. We get, I don't know what else in my notes, 36. Or excuse me, 32. And 32 minus 3, we get 29. So we have f composed of g of 1 equals 29. What was great is that those questions on the test that you had to answer in function notation, most of you remembered to answer in function notation. So that's good. Yeah? You can do that as well and just plug it in. Yep. The reason why I don't do it that way, because I like you guys to practice forming the composite and then plugging it in. But yeah, that's totally cool too. Do you think you could do B? Yeah, go ahead, try. Yeah, go ahead and try do B. All right, so for B, we're putting f inside g. So that means we're putting all of f inside g for every x we see. So we have, g composed with f, or goff, I like to say, goff and fog. We're going to put it in. We have 4 times x, which is 2x squared minus 3. And that's all the only x we have, so we just keep going from here. Now we have 1. What are we going to do with that 1? Plug it in. Yep. So we have 4 times 2x, which is 1 squared, minus 3. We just simplify inside the radical. So we do 4 times, so 1 squared is 1. 1 times 2 is 2. And 2 minus 3 is negative 1. And we keep multiplying. So g composed with f of 1 equals negative 4. So how'd you guys do? Did okay? All right, close. As long as you got close, you just learned this. So I'm proud even if you got close to it. Any questions for me at all before we move on to C? You like my terrible X's that I drew there? I used a computer, I didn't use my tablet. I was too lazy to go get my tablet when I made this. But yeah, those are supposed to be X's. So no longer we have 1s, we're just working with X's. Now let's form our composite for C. So part C, we have F composed with F. And I'm going to rewrite F down here. So we want to do F composed with F of X. So what are we going to do with F? Yep, we're going to plug it into itself. Things are going to get weird. So we have 2 times x, which is our function. So 2x squared minus 3. And that's all squared, minus 3. So you notice this time it's just an x, not a number. So you just simplify as much as you can. So to simplify, we are going to square 2x minus 3. And remember that that is 2x minus 3 times 2x minus 3. And when you do that, we have 2 times 4x squared minus 12x plus 9, all minus 3. So just some foiling.
Well, where does the squared in the middle, like in the red, go?
Oh, sorry, it's supposed to be to the 4th. 4th and squared. There we go. So, what should we do next? Yep, multiply by 2, distribute it. So we get 8x to the 4th minus 24x squared plus 18. Ooh, my bad. 18 minus 3. And then last but not least, we combine like terms. So we get FOF, or f composed with f of x, equals 8x to the 4th minus 24x squared plus 15. That's ridiculously long. There we go. It's totally cool if in class you want to say FOF and GOG and FOG and stuff, because f composed with f is just a mouthful. You have any questions for me? All right, I totally believe you. You ask questions when you need it, because your test results state that.
What
So,
did you say the little terminal was again?
say again?
Terminology for the circle?
Oh, it's f composed with f.
Composed.
Yeah, composed with, yeah. All right, you want to move on to part D? All right, cool. All right, part D, we're doing G composed with G of X, so GOG. What are we going to do with G? Yep, plug it into itself. So we have G of X equals 4X. So all we're doing is just plugging it inside itself. All right, let's do that. So we have 4X, which is 4X. So we simplify to get G composed with G of X equals 16X. Sometimes composites are super easy. Sometimes they're tricky and long.
So when we do our answer, it has to be G composed with GX.
Yeah, it has to be in function notation. Yep. So just remember, if I'm doing it, it's because you have to do it. It just lets the reader know that you're working with composites, you're working with functions. So they're not just there like, what does this mean? What does 16x mean? Although the average reader would know what that meant, because who's reading math for fun? You're not me. I bought this book over the weekend called Burn the Math Class. And it's a math professor who wrote a book about how we should deconstruct how we teach math completely because it's awful, and I totally agree with that. And it has all this math stuff in it. I'm like, oh, this is just wonderful. Yep. So, all right. Can we go on to example 2? Cool. All right, example 2. I have no idea why. It's supposed to be 1, but it's not there. But it's supposed to be 1 over x plus 2. So we want to find composites. Suppose that f of x equals 1 over x plus 2, and g of x equals 4 over x minus 1. And we're also going to find the domain. We're going to start finding the domain now. All right, so part A. Part A, we have f composed with g. So we're going to plug in g inside f for every x we see. There's only one x, so that's where we're going to plug it in. So we have 1 over x, which is our g of x, so 4 over x minus 1 plus 2. Now you notice there's no x here, there's no 1 or anything. If there isn't any of that, it's just x. So you're going to simplify it. This is a complex fraction. We absolutely hate it, but we can get rid of all of these weird fractions by multiplying by something. What do you think we should multiply by? X minus 1. Yep, we're going to multiply everything by x minus 1. Because when we do that, you notice it cancels these out. So we're no longer working with a weird composite, or complex fraction. So we do 1 times x minus 1 is just x minus 1. And then we have 4 left on top. So 4 plus, we distribute the 2, 2x minus 2. Can we combine like terms here? Yep. So we have x minus 1 over 2x plus 2. Is this simplest form? No. How do we get into simplest form?
Factor?
Not take out the negative 1. Yeah, what are we going to factor?
Factor it out, the 2.
Yep, we're going to factor out the 2. If it were negative, like negative x minus 1, you would take out that negative. So yes, that is simplest form. So that is f composed with g. You have to make sure that that denominator is factored, because that's what simplest form means. So let's put it in your notes. So yeah, make sure that your denominators are always factored. So before we move on to the domain, are there any questions on how we formed this composite? Okay. Cool beans. So we are going to find the domain. And just to remind ourselves, we did f composed with g. So to find the domain, you find the domain of the second one, and then the composite as well. So for g of x, what can x not be? So for g of x, if you put something in that x to make it 0, what would it be? 1. So that means the domain of g of x cannot be 1. All right. What's the domain of f of x? Yeah, you don't have to whisper it. Yep, it's 2. So part of the domain is x can't be 1, but we need to do something special to that too. Whatever the first letter of your function, whatever that domain is, you set the second function equal to that. So the domain, remember we're doing f composed with g. So our g of x, our second letter is g of x. So g of x is 4 over x minus 1. And then we're going to set that equal to the domain of f of x, the first letter. So 2. So that's what that was saying on the first page. To find the domain, it's the domain of g of x, which is the second one. In this case, we say g of x because on the top, it's f composed with g. But it's just that second letter. And then you find out the domain of the first letter and equal it to the second letter. And we solve for x. So what do we do to solve for x? Yep, multiply it by the denominator. So when we do that, it cancels them out. And then we're left with 4 equals, we're going to distribute the 2, 2x minus 2. We're going to solve for x. So we add 2 to both sides. We get, yeah, that's right. Did I write this wrong? It's supposed to be it's supposed to be negative 2. That's why that's wrong. There we go. All right, sorry about that. I didn't catch that. Yeah, it's supposed to be negative 2 because if you plug in negative 2, it makes it 0. My bad. So we have negative 2x plus 2. We subtract 2 to both sides. So we get 2 equals negative 2x. Divide by negative 2 to get negative 1 equals x. So now the domain is whatever the second letter domain is, and then the domain you just found. So the domain is, how did I write this? X such that x cannot be 1 and x cannot be negative 1. So just to talk about the domain again, you find the domain of the second letter, that's part of that domain of the composite. So after you find the domain of the second letter, you find the domain of the first letter and equal it to the second one. Oh, my bad, can't. Cannot be. I gave you a lot of practice with this, so hopefully it's not too bad. I know that's the tricky part about composites is finding that domain. Do you have any questions for me? So composites, like, pretty comfortable with them? Okay, so we'll do the next composite together, and then I'll have you find the domain of it. I want you to practice that on yourself. On your own, not on yourself. That's weird. You can't practice finding the domain on yourself. There's no domain there. All right, so for B, we want to do f composed with f, so fof. And I'll just write f of x again. So what we're going to do is we're going to plug the function inside of itself for every x we see. So we have 1 over x, which is 1 over x plus 2. and all of that plus 2. Now, what should you multiply by? X plus 2, good. If you took me for intermediate algebra, I taught you to always cancel out your fractions, and this is a big reason why. All right, so they cancel out. We're left with 1 times x plus 2 is x plus 2 over, so 1 plus, we're going to distribute the 2, 2x plus 4. Should we combine like terms? Always. So we have x plus 2 over 2x plus 5. Can we simplify that? Anything in common on the bottom? Nope, can't. So that is it. That is f composed with f. So now I want you to spend some time and find that domain. So find the domain of f and then set that equal to f. It's a special one. So find the domain of your first letter, or excuse me, of your second letter, then set, that's part of your domain, and then whatever the domain of your first letter, you set it equal to the second one. In this case, it's f of f, or f composed with f, so you just set it equal to f. We have our function f of x is 1 over x plus 2, so what can you not put in there? What can't go there? Negative 2, right, we already had that. So we're going to set it equal to our f of x. So just to kind of reiterate that, we're doing f composed with f. So you find the domain of f and then set it equal to the first one. And then we solve. What would you multiply by? X plus 2, good. So we distribute this negative 2 to get negative 2x minus 4 equals, these x's cancel out, or excuse me, the denominators cancel out. And we have equals 1. So we add 4 to both sides. We get negative 2x equals 5. Divide by negative 2 to get x equals negative 5 over 2. So that means the domain of everything is whatever the domain of the second letter is, which is negative 2, and then whatever the domain you found after you set it equal, so negative 5 over 2. As long as you can find the composites, the domain will come.
Is there a different way to do that, or did I just get lucky?
How'd you do it?
I used f of f, x plus 2 over 2x plus 5, and then set the bottom to 0.
That would, yeah, no, that would work the same.
Okay.
Yeah, just because they're both the same. So if they're both the same, totally works every time. Yeah. That's funny. Did I just get lucky? That's something you have to ask yourself in math class. Was that just a coincidence, or did I mean to do that? Got it. Any questions before we move on to example 3? All right, let's move on. All right, so something a little different. We're still working with composites, but we want to show that these two composites equal each other. And we do that by seeing, can we get them both to equal x? Because if you have two things, they might look different, but if they equal x, don't they equal the same thing? Mm-hmm. Just remember that. If you're going on to higher level classes, just remember that. They might not look the same. You might not be able to get it to look the same, but if you can simplify it down to one thing that is the same, then it is. Okay. Trig, especially trig with identities, chapter 9. Well, it used to be chapter 9, it's not anymore. If anyone's going to trig, when you get to identities, please come by my office so we can cry together. All right, so we want to show that f composed of g of x equals g composed with f of x equals x. So we're going to try and reduce these each down to x. All right, our first one, we want to do f composed with g. So we're going to put g inside f. So f, we have 3x. That's what's going to go in for the x we see. So we have 1/3 times x plus 4. And that's all minus 4. Do you see anything that can cancel out? Yep, the 3 and the 1/3. Because that is 3 over 1. And since we're multiplying this, you can go ahead and cancel them out. So I'm going to write what we have left over. We have x plus 4 minus 4, which equals x. So we got it to equal x. Good. Should you ever assume, just because they look alike, that they are alike? No. Don't assume in math, remember. Okay, let's do the second one. So we're doing g composed with f. That means we're going to put f inside g for every x we see. All right, we have 1/3 times x, which is 3x minus 4. And that's all plus 4. Can you cancel out the 3's again? You sure? What's the difference between them? Well, no, you can still do it if it's just x. No, we can make it 3 over 1, but good thinking. Yeah, because of those parentheses. That's 1/3 times. This is 1/3 times 3x minus 4 plus 4. So don't we have to simplify the parentheses inside before we do anything? That's the difference. Okay. So we simplify, we get 1/3 times 3x because the 4's cancel out. Now can we get rid of the 3's? Yes, now you can. So we have 1 times x, which is x. Do those both equal x? Yep. So to verify this, your work is your answer. So there's no boxing anything. It's just showing your work. Okay. Any questions for me? None? Alrighty. I believe you. We're going to save example 4 for last today. Okay, we're going to save that for last. We're going to move on to 6.2. All right, so 6.2. One-to-one functions and inverse functions. So determine whether a function is one-to-one. When you think of one-to-one, what does that mean? One goes to one, yeah. So you can't have this pen go to the water bottle and mouse, right? That's not one-to-one. One-to-one. Okay, perfect. So basically a one-to-one function is each x in the domain has one and only one image in the range, meaning one x to one y and vice versa. So in example 1, we're going to look at the charts and determine if they are one-to-one functions. So is the left one one-to-one? No, right, no. There's arrows going to multiple things, right? What about the second one? Yes. Yes, and there will be those easy questions on the test as well, so please get it. All right. Another way to determine if something is one-to-one is using the horizontal line test. So we have vertical line test. It determines if it's a function or not, but a horizontal line test actually tells us if it's a one-to-one function. So what you do is you create horizontal lines, and it works the same way as the vertical line test. If you have two values that cross the line at the same time, it's not one-to-one, because that means if this was -3, 4, this would be 3, 4. You see how the 4 goes to two x's? That's why it's not one-to-one. All right, so example 2, I actually drew everything for you and all of that. Look at that, that's nifty. Is f of x equals x squared a one-to-one function? No, all parabolas are not one-to-one. That is a terrible no. What about b? Yes, it is. Are circles one-to-one? No, they are not. Good. Why is it one-to-one? The middle is, and you can't really see it, but it's supposed to go up like this. It doesn't actually, it's not horizontal at all. Okay, yeah. Totally messed that up. Oh, what? Hold on. There we go. All right. Control Z. I remember when I discovered that when you first take typing classes in school, and you press it by accident, and you're like, what happened to everything? You just press Control Z. All right. Yeah, I took typing classes with the original Apple, and I played Oregon Trail on that crap, man. It was so fun. I love 3rd grade. All right. Miss Brandman, I'll never forget her. You have those teachers you just never forget. She's one of them. All right, so inverses. Determine the inverse of a function defined by a map or a set of ordered pairs. So basically, an inverse is you switch the x and the y's, because inverse means opposite. The opposite of x is y, and the opposite of y is x. So for example 3, before I move on, that's what this is saying. And to state it's an inverse, so if you want to say to someone that's reading this that that's actually an inverse function, you do f, and then it looks like to the power of -1 of x. So that means you have an inverse, and it lets you know you just worked with an inverse or you found the inverse. So for example 3, how would we find the inverse? You would just switch all the x's and the y's together. Yep. So we have -27, -3, -8, -2, -1, -1, 0, 0, 1, 1, 8, 2, and let me write that on the bottom, 27 and 3. Bless you. I'm not going to have you state the domain and range because we have a lot of numbers, but remember the domain is just list all the x values, and the range you would list all the y values separately. Any questions for me? already. I love your polar bear thing. Every time I see it, I'm like, just makes me happy. Have you guys been to the Coke store thing at downtown Disney or Disney Springs? It's really cool. It's like 3 stories of Coke merchandise. I can spend so much money there. It's really cool. You should check it out. And on top, at past 7, you have to be 21 to get up there. They serve like a whole bunch of alcohol with Coke in it. So like it's like mixed drinks with Coca-Cola. It's really good. They have a Frank Sinatra Coke or a Frank Sinatra whiskey with Coke. It's really good. If you are 21 and up, go do it. If you're not, sorry. You gotta wait. Okay, so we'll talk about the domain when we actually go over it, because reading that, right, the inverse, right, none of that makes sense to you. That's math talk, so I'll talk about it when we get to example 4. One thing that's really cool about inverses is that they're symmetrical over the y equals x. So if you graphed y equals x, so if you just graphed it, it looks like that. It's the one that goes straight through the middle. So if you fold it over that line, they are symmetrical. So that will come up later today. All right, example 4. Verify that the inverse of f of x equals 1 over x minus 1 is f of negative 1, or excuse me, the inverse equals 1 over x plus 1. For what values of x is, so when you plug in the function inside the inverse, equals x. And then for what values of x is, when you plug in the inverse into the function, equals x. Now that all seems very, have no idea what's going on. That's fine. When we work it, it gets a lot better. So the first thing we're going to do is find the domain of each of these. So what's the domain of f of x? What can't go here? 1. Yep. And then what's the domain of the inverse? What can't go there? What makes that 0? 0. That's a trick question. It's just 0. Yeah, so always do that first. Even if it asks or not, just write that domain. You'll see why later. All right, so for the first one, it's asking us to put the function inside the inverse. So if this was g of x, it would be f composed of g. So that inverse, if we named it g of x, if that had a separate name, then all we're going to do is plug it in. Or excuse me, it's different. It'd be g composed with f. That's the second one. So we're plugging the function into the inverse. But it's not g of x. We're not going to call it that, but that's exactly what we're doing. That's why we learn composites first. So we have our inverse composed with our function. So our inverse, we have 1 over x. X is our function, so that's 1 over x minus 1. And that's all plus 1. What do we do to get rid of that weird fraction over the fraction? Multiply, right? We multiply by x minus 1. And you notice I'm only doing it to the fraction itself. You don't have to do it to everything because we're just trying to simplify this. So we have x minus 1 over, those cancel out, 1 plus 1. Do we need that over 1?
No.
Nope. So we have x minus 1 plus 1, and that equals x. What can x not be for f of x? For f of x. 1. So we exclude 1 because you notice we're putting the function inside the inverse. So if the function's 0, what makes the whole inverse? It makes it 0. So that's why we only care about what matters when we plug it in. Because that's what the domain is when you plug it in, what do you can and cannot get. Are there any questions for me so far? Do you want to try one? We're not done yet. We want to try. Oh, you have a question?
Why is it excluding one?
So we're putting the function inside the inverse. So if the function is 0, because that's what we're talking about, the function right here, it can't be 1. So if we plug it in and it's 0, can you have 1 over 0? That's why we have to exclude what you're plugging in. Okay. That's the only time you exclude is what you plug in. So for the second one, maybe you see it, maybe you don't. I'll point it out to you. It's right here. So the second one, we're plugging the inverse into f of x. So go ahead and plug the inverse into f of x and let me know what it can't exclude. Or what it has to exclude. So we're going to plug in the inverse into the function. So we have our function 1 over x, and that's where we're going to put the inverse. So 1 over x plus 1 minus 1. All right, let's do some simplifying first. We have 1 over x, because the 1 and 1 cancel out. Do you know the trick about this? Yeah, you just flip it. So you see how it's 1 over something? Anytime it's that way, it's just the denominator. Another way to have done that was multiply everything by x, but it's just faster to know that you can do that. So if you didn't remember that, you'd multiply everything by x. So these cancel out, and we're left with 1 times x is x, and that's x over 1, which is just x. What are we excluding, though? Yep, 0. We're excluding 0 because that's the domain of what we're putting in. So again, it says to verify all of your work is the answer. There's nothing to box here. If you need to box something, I feel you. I'm the same way. But there's nothing to box here. It's just, box the whole thing. I actually saw some of you box the graphs and stuff like that. Thank you. All right, do you have any questions for me at all? Or do you want to move on? Move on. All right, finding the inverse of a function defined by an equation. So basically finding inverses of a function. All right. So here's the math talk, and then of course, I'm always going to give you the real talk. Procedure for finding the inverse of a one-to-one function. In y equals f of x, interchange the variables x and y to obtain x equals f of y. The equation defines the inverse function. If possible, solve the implicit equation for y in terms of x to obtain the explicit form of the inverse. And check the results by showing that when you put them into each other, they both equal x. And yes, you always have to do that. Because, you can find the inverse, but does it actually have an inverse? So you need to check. Math, this is where it starts to lie to you sometimes. All right, first, so what that means, all that means is you switch x and y and you solve for y. That's how you find the inverse. To check it, we did that in example 4, but we'll do it again because we need to check every time. So f of x is the same thing as y, so we have y equals 2x plus 3. And to find the inverse, you just switch them. So we have x equals 2y plus 3. Now solve for y. So to solve for y, we subtract 3 to both sides. We have x minus 3 equals 2y, and then divide everything by 2. So we have x minus 3 over 2 equals y. Now you need to let the reader know that that's an inverse. So it would be x minus 3 over 2 equals, and then just function notation stating that it's an inverse. So, in my opinion, that is a perfect answer. It's absolutely perfect. But others will argue that this is actually the answer. Which I understand why, because it's technically simplified more. But,
Does that mean that my math lab will prefer this one?
yep, that's what I was about to say. My math lab is going to want that one. Yeah, so on my math lab, make sure if it's under 2 or over 2 or over 3, you just put a 1 in whatever the denominator is and bring it out. So that's just finding the inverse. That's great. You can always find an inverse, but it doesn't mean one exists. So to check to see if it exists, you're going to do what we did in the previous example. You're going to put the function inside the inverse, and then you're going to put the inverse, my bad, inside the function. All right, so let's do this. We're going to put the function inside the inverse. Now, when you work with the inverse, you can use the x minus 3 over 2 because you're going to eventually get to that anyways. So let's use that. We're going to put the function inside the inverse. So the function, we have 2x plus 3. So x, right here, x, that's the function of 2x plus 3. And we're going to subtract that to 3. And that's all over 2. So we simplify. The 3's cancel out. We have 2x over 2. The 2's cancel out. And we have x. That's our goal.
Wait, can we back it up?
Yeah, go ahead. Yep. Just go over again?
Yeah.
All right, cool. So you always have to check to see if it actually is a function. To do that, you plug them into each other. So we plug in the function into the inverse. And we did that. So we plugged the function into the inverse and try to simplify down to x.
The half through.
Oh, yeah.
And this is to check yourself?
You always have to check it, yeah. Are we okay so far? Still doing okay? All right. So now we need to check the second one. That one right here. So we're going to put the inverse inside of the function. And the inverse I'm going to use is x minus 3 over 2 because it's just easier to use that. So we plug it in. We have x, 2x. So 2 times x, which is the x minus 3 over 2. And that's all plus 3. Are you able to cancel out those 2's?
Yeah.
Yes, you are. So we get x minus 3 plus 3. The 3's cancel out. You're left with x. So does it check out? Yep, that is an inverse.
And that's part of the answer. You have to have that when we fill out.
Yeah, you do. Yeah, you have to check it. Just because, like I said, you can have inverses, but doesn't mean it actually exists. Right, you can say anything in math, in life. You can say it, but it doesn't mean it exists. All right. So finding the inverse, you're doing okay so far? Checking it? That's a whole different story, huh? Yeah.
Yeah, I'm more confused. You know what I think screwed me up was there's two equations. And you have the x minus 3 and then the other one.
Yeah.
They're confused.
Well, they're
I
the
know- I know
yeah,
what
they're
you're
the same
saying.
thing, but yeah, I can
They're
see how that's
confused a little
confusing.
bit. Sorry.
No, don't be. That's fine. It is. This is not easy. It's confusing. Want to do it again? We have a whole nother one to do. We're going to do the same exact thing, except it's a different problem. All right, let's go. Let's do it again. So, the function is 1 to 1. Let's find the inverse and check the results. All right, so we're going to change f of x to y. We have y equals 2x plus 1 over x minus 1. So now we're just going to change the x's and the y's. So we have x equals 2y plus 1 over y minus 1. If the checking part is what like really kills us, I will state on the test if I want it to be checked. If it doesn't, you can go ahead and skip checking it. Because I'm not going to have you check every single inverse. That's a lot of time. All right, we need to solve for y. Anytime there's a variable that we need to solve for in the denominator, what do we do with that denominator? Yep, we multiply it. Good. So we multiply it. Those cancel out. We have y times x is xy, and x times negative 1 is negative x, and that equals 2y plus 1. So we're trying to solve for y. If we're trying to solve for something, you should try and get all of that to one side as much as you can. So what I mean by that, we're going to add x over, and then we're going to subtract 2y, because I want to try and get the y's on one side. This way I can get them alone as much as I can. So we have xy minus 2y equals x plus 1. What's great about inverses is every time that type of problem, it'll always be the same. Every step will be the same. You'll notice that on your homework. So for example 5, the first thing you did was subtracted a number and then divided, or add and subtract then divide. So for a linear function, to find the inverse, you're going to add or subtract and then divide, always. If you have a rational function, the first thing you're going to do is multiply the denominator, move over the variable to one side, and then you'll see what we're going to do next. Do you see anything in common? Why? So let's take it out. Can we get y by itself now? Yep. Divide by x minus 2. So we have y equals x plus 1 over x minus 2. Every time you have a rational function, so a fraction like this, every step is going to be the same. It's just going to be different numbers. It will never, ever, ever be different. before we check, do you have any questions on how we found the inverse? That's the most important thing today right here. It's just finding that inverse. Comfortable with that? All right. Okay, so to check it, we do the function inside the inverse, and then the inverse inside the function. So we're going to put the function inside the inverse. We have our inverse of x plus 1 over x minus 2. So x is the function we're going to put into it. So that's 2x plus 1 over x minus 1, and that's plus 1. And that's all over x, which is our function of 2x plus 1 over x minus 1 minus 2. Isn't it kind of neat how everything is starting to scaffold? We started evaluating and then adding functions together and stuff like that. Then we composite them. Now we're doing this. What would you multiply by? Yep. So those x minus 1s in the denominator cancel out. So we're left with 2x plus 1 plus, so 1 times x minus 1 is just x minus 1. And that's over 2x plus 1. We're going to distribute the negative 2, so we have negative 2x plus 2. We combine like terms on top, which is 3x. We combine like terms on the bottom, it's 3. Those 3's cancel out. We're left with x. That's a really nice 3. I had to erase it just to show myself again. You think I'd be better at writing numbers because it's what I do for a living? But it's not. It's not true. All right. Darn. I was going to have you do it on your own, but we're kind of running out of time, so we're going to do it together. We have to check the other one now.
Why did you get it?
Oh, sorry, go ahead.
Why did you get the other three?
You see how there's like no adding or subtracting in between the x's, the x and the 3?
Yeah.
So because there's nothing like that, you can cancel out top and bottom if they're the same. Right here?
Where'd you get the bottom three?
Oh, how to get the bottom 3. Okay, so 2x minus 2x cancels out, and then 1 plus 2. Okay. All right, for time purposes, this does check out. I'll tell you that. It works. Let's move on. I want to make sure we try and get to everything we can today.
Should we gonna just pass over the 6.1?
No, we'll get to it tomorrow or Wednesday. Yeah, we'll get to it. Chapter 6, if you notice, we take everything almost day by day. So we have a lot of time to, if we need to finish the next day, it's totally fine. It's called padding your schedule. I learned the actual term for that the other day. I didn't know it. All right, so example 7. The graph of a one-to-one function is given. Draw the inverse function. All right, the best way to do this is let's list the points of f of x. You don't need to. You can do this in your head, but I'm just showing you. So the point of f of x is -2, -2, 0, -1, 1, 0, and 2, 1/2. So if that's the function, how do you find the inverse? Yeah, you just swap them. So the inverse, well, negative 2 doesn't change. Then we have negative 1, 0, 0, 1, and 1/2, 2. All you do is just plot these points now. So negative 2, negative 1, 0, 0, 1, and 1/2. It's about right there. So if you notice, if you fold it over this line right here, that y equals x, they're on top of each other. All right, we have one more example. We're going to get to it because we have 4 minutes left, or 3 minutes left. And then on Wednesday, we're going to start with the last example of 6.1. Because it is part of your homework, and it'll be a part of your test. Are there any questions? All right, let's keep going. Example 8. So the domain of a one-to-one function is 5 to infinity, and its range is negative 2 to infinity. State the domain and range of the inverse function. So if you just switch the x's and the y's, what do you think we should do to the domain and range? Yeah, you just switch it, yeah. So the domain would be negative 2 to infinity, and the range would be 5 to infinity. Is that just a nice, neat... Yeah, that's it. Done. Yeah. This question is just testing, do you know the concept of what an inverse function is? It's just switching the x's and the y's.